Look at chapter 17 on sampling distribution. I will say this is one of those things that greatly confused me at first, but I think I got it down, and these notes are my distillation of figuring out how this actually works. So, we're going to look at an example that'll help you understand how sampling distribution works. So, let's say that a particular microchip manufacturer finds that 20% of the chips they make are defective. Yes, I know that's a ridiculous number. It just makes it easier to do this, right? They'd go out of business. If we were to sample 10 chips, we would expect to find 2 of them were defective, right? Two being 20, he went, oh yeah. But if you're taking a random sample of 10, is it always going to be 2 that are defective? No. Sometimes you may find more. Sometimes you may find less. Okay? So we use P to stand for the parameter of the model for proportions. P is the probability of success. Now, success in this case is the proportion of is 0.2, the proportion of defective chips. So remember, we talked earlier last semester about success isn't always a positive thing, right? So now let's suppose we were to look at all possible samples of size 1, right? If the manufacturer produced 1,000 chips in a day, then there should be 800 that are fine and 200 that are defective, correct?
Yes.
And if we're looking at all the possible samples of size 1, well, there's going to be 800 samples that have 0 defective and 200 samples that have 1 defective, right? And again, yes, I know that's ridiculous, but we're kind of building to something that's not ridiculous. Okay? So the observed proportion of chips that were defective for this was 1, and for this smaller one, was 0, and for this was 1, right?
Wait, so what does the 0 and 1 mean?
How many were defective? In 800 samples, so this is how many samples,
Yeah.
there were no defective chips. And in these 200 samples, there was 1 defective chip.
Yeah.
Okay? So again, this isn't a random sample. This is, I took every possible, sample of size 1. It's going to look like this, right? Well, what if we took samples of size 2? It turns out, and you could actually work this out, but it takes a little while to do it, you would only have 40 where one of them was defective, where all of them were defective. So the 1 is going to be all of them. The 0.5 would be half of them were defective. The 0 is going to be none of them are defective. It turns out that there's only 40 ways that you can have out of those 1,000. If you're doing samples of size 2, there's a whole bunch of different samples that you can get, but there's only 40 of them where both of them are going to be defective. And your histogram kind of looks like this.
So what do they mean by like size 2, size 1, size 3, and size 5?
That's how big your sample is. So I'm going to take the 1,000
Yeah.
and I'm going to do all the possible combinations I could get.
Yeah.
Chip 1 with chip 2, chip 1 with chip 3, chip 1 with chip 4, et cetera, et cetera, et cetera. So there's a whole bunch of those, right? So those are the samples of size 2. There's going to be 640 where none of them are defective, 320 where half of them are defective, and 40 where both of them are defective. Then when we get to a bigger sample size, notice it's getting harder and harder to get it to where all of the chips are defective, right? If you take a bigger sample, if there's only a 20% probability of getting a defective chip, then that number keeps going down, right? The probability of getting everyone, let's say I took a sample of size 100. Well, the probability of getting every one of them to be defective would be 0.2 to the 100th power. That's a tiny number, extremely close to 0. Okay? Also notice that when we start getting here, now we start to get, okay, when we got to a sample size of 0.2, this is the first time we had 0.2 as a possibility, that 20% of the chips were actually defective. Well, that should be the one that's the most, right? That's the most likely thing to happen, is that 20% of the chips are going to be defective. So none of the chips defective is less than that, and notice that all the chips defective has basically disappeared. It's possible, it's just not very likely. So if we were to do a weighted average for these, it would always come out to be 0.2 still. But as the size of your sample increases, the amount of variability actually decreases. By the time we get to sample size 5, like I said, it's basically impossible to get a proportion of 1 where every chip is bad. Now let's turn it over and look at the next page. This is where it starts to get interesting. We do a sample of size 10, and you're like, okay, 0.2 should be the one that happens the most. And it really falls off over here to the place where even getting 70% of the chips defective is almost impossible. Here, I skipped over a whole bunch and went to, what if we did a sample of size 50?
Can you explain the sample size again?
That's how many you're taking in your random sample.
So it would be 1,000.
Out of the 1,000, I'm choosing 10. And I'm doing that over and over and over again.
Okay.
You sure? Because this can be a little weird. So there are 1,000 chips.
Yeah.
I'm randomly going to select 10 of them. I'm going to
And that's
record. That's your first sample, but your sample size is 10.
Okay.
I picked 10,
And then based off that,
and I record what proportion of them
defective.
were defective.
And then you do.
And then I put those back in, mix them all back in, pick another 10.
Oh, okay.
That's from that same 1,000.
I get it now.
Yeah, from the same 1,000. I just keep doing that with replacement over and over and over again.
And now it makes sense of why they keep getting. Okay, yeah.
Right. And so as I do that over and over again, I should get the most likely should be that 20% of them are defective.
Mm-hmm.
But I could also get that 40% of them were defective. Right? It's not a ton of them, but it's possible.
Yeah.
It's not crazy. When we get to the place where we've done that 50 times, what kind of a curve does this look a lot like? Unimodal.
Normal.
Looks like a normal curve. Right? It's unimodal and symmetric. So it's unimodal and it's centered about 0.2. This is a normal distribution, and it's called the sampling distribution model. A A sampling distribution model shows how a statistic, in this case, the proportion of defective chips, varies from sample to sample. Because not all of our samples are going to have exactly 20% defective, are they?
No.
There's going to be some variability in that. Okay? And that's what this shows, is the likelihood of getting, I'm going to have to make this a lot bigger, but the likelihood of getting 32% instead of 20% is pretty small. Right? So, we've already shown that the mean of the proportion of the sampling distribution mean is the mean of the population. In other words, the mean of p hat is equal to p. Remember, this is the mean of the observed proportions is going to be equal to the proportion from the original group, if you do it enough. The standard deviation, it's a little bit more complicated. You may remember that for a binomial model, the standard deviation of the number of successes for n trials was the square root of NPQ. Since the sample proportion p hat is the number of successes divided by the number of trials n, then the standard deviation ends up being the square root of NPQ divided by n, which is the square root of PQ over n. So, when we draw random samples of n individuals, the proportions we find will vary from sample to sample, right? Not all the samples are going to be the same. This is called either sampling error or sampling variability. I kind of like calling it sampling variability rather than sampling error. Sampling error makes it sound like you did something wrong in your sample. It's just that your sample doesn't give you the true proportion of your whole population. So as long as n is reasonably large, we'll talk about how large in just a moment, we can model the distribution of these sample proportions with a probability model that is the normal model, where our mean is going to be the proportion of the population that are, in this case, defective, and the standard deviation will be the square root of PQ over N.
Is this on our grade sheet, or do we have to memorize?
So, yeah, that's what I was about to, let's look at that. I think it's on the back. I'm not positive. Yeah. I think it's that first one.
Oh, yeah.
So it says, for one population, p hat, the mean of p hat is equal to p.
Oh, yeah.
And the standard deviation of p hat is the square root of, they don't do pq, they do p times 1 minus p, which is pq, over n. That's your standard deviation. So this is not one that you have to memorize.
Okay, so there's.
You're going to use it so much that you probably will, but
And then the p hat is like the y hat one we learned at the beginning. So you'd
not
have.
quite.
Oh, okay.
But the p hat is the observed proportion.
So 0.2 would be the p hat.
No, p
Oh,
is 0.2.
P hat would be the count number. Oh.
P hat would be the proportion that we observed. 0.4, 0.5, point whatever. So we take a sample,
Mm-hmm.
and let's say that we took a sample of 10 and 3 of them were defective. Our p hat for that sample is 0.3.
Okay.
It's the observed proportion that are whatever characteristic that we want.
Okay.
Okay?
So p is always for like sample one. Like if
No,
you're taking
p is for the entire population.
one. Okay. And then.
P hat, so p is the proportion of the entire population.
And
That,
in a sample of one, in a perfect scenario, it would be the same as p. Like p hat, and p would be the
In a sample of size 1, p hat will never be 0.2.
Why not? I thought it was in the first one.
Nope. What were the two possibilities? Either they're all defective or none of them are defective.
Oh, it's one, not okay.
Yeah. Okay.
Yeah.
So there was a difference between this standard deviation and that standard deviation, or sample error.
So the standard error of the statistic, we'll get more to that later, but it's the same thing.
Oh, okay, that makes sense.
This is hard.
Because
Just a little.
p hat and p, if you have a sufficiently large number, are going to be the same.
Yeah. That makes sense.
Okay? So, what are the assumptions? This is one of those things where you have to memorize, and you need to be able to just regurgitate this back. Okay? So, and this is going to happen a lot this semester, and the thing that makes it difficult for me at least is that several of them are going to be pretty close. They're not quite the same, but they're pretty close to the same. All right, so what do we have to look for in order to be able to use this normal model? All right, so, and the normal model, by the way, would end up being this. It's a normal model where the mean proportion is 0.2, and the standard deviation of the proportion is 0.0566. Okay, that's with 50. You know, like
Oh, okay.
with a sample of size 50. That's what we're going to get. So we have 3 different things we have to look at. First of all, the randomization condition. If you're doing an experiment, remember, an experiment requires randomization of assignment of treatments. That's for an experiment. Most of the time, we're not doing experiments. Most of the time, we're taking a survey where, and you know, again, people tend to think about surveys as where they ask you stuff. A survey is from our perspective, we're the surveyors, so we're gathering information. Okay? You got to use random samples. The independence assumption. So in most cases, we really can't know if our sample is truly, if one is truly independent of another one. But you can look how the data is gathered to see if it's plausible. So sometimes I'll actually say, you know, given that they gathered the data this way, it seems that it's plausible that these are independent. If we sample too much of the population, the individuals may no longer be independent. That's the one where it's like there's 1,000 boxes of cereal. We picked one out randomly, and we don't replace it to look to see if there's whatever toy surprise we're hoping to get. But because we've taken out such a small number, we're not really affecting the probability that we're going to get one at any given time. When you get to over 10% of the population, it starts to be more likely that you have messed with the independence. So we use the 10% condition. The sample size needs to be less than 10% of the population. Most of the time, that's a pretty easy thing. You just go, yeah, we sampled 450 American women between the ages of 18 and 35. You know, that's less than 10% of the entire population of American women between 18 and 35. Then we also want it to be big enough. So you don't want it to be too small, but you don't want it to be too big either. So the sample size assumption is the success-failure condition that we used briefly last semester, where we want the expected number of successes and the expected number of failures to be at least 10. So NP is greater than or equal to 10, NQ greater than or equal to 10. We want both of those things to be true. Okay. And these conditions, you were talking about what formulas are available. The formulas are on there. The conditions are not. So you got to know the conditions. If you don't know the conditions, things will go badly.
Do we say like the independence assumption is plausible for this or sample because or no?
You might want to write just independence and then go, given how this survey was taken,
The sample size is
well, we can assume that it's likely that they're independent and they used less than 10% of, and be specific, in the context of the problem,
yeah.
they used less than 10%.
Okay.
All right, let's at least start this one. What time is this class over? 15? Let's go ahead and start this example. So we've got a high school with 2,000 students. 30% of the students have a driver's license, which is probably a reasonable number in any given high school, right? If you're doing 9 through 12. Suppose we select a random sample of 50 students and determine whether or not each has a driver's license and calculate the proportion of students that have a driver's license. So we're finding a sample proportion. We're finding what proportion of, and I don't know about you, but it bugs me that they say proportion. My math brain says they should be saying percentage. But when they say proportion, they're really saying what percentage. Okay? So we're going to determine the percentage of students that have a driver's license. What's the probability that more than 40% of the students claim to have a driver's license? Be sure to check the conditions and assumptions necessary. So we're going to try to apply a normal model to this. What are the assumptions? Well, right up here. So, is this random? Well, it says right at the outset.
Yes.
So, 1, the problem specifies that we select a random sample. And I know it's a lot of writing, but don't get lazy on this. On the AP exam, if you do random, check mark, independent, check mark, you're just going to get killed. Okay? The second part, independence. All right. So we can't know for sure that one is independent of the other, right?
No.
But it seems reasonable to assume that each student driver's license status is independent. And 50 students is less than 10% of the 2,000 student population.
the 50 students is less than 10% of the 2,000, I thought that's what makes it reasonable to assume that it's independent.
So yes and no. One of the things you check is that you don't have too many, because having too many will cause it not to be independent, but it's possible they're not independent for other reasons.
Oh, okay. So other than the 10%, then what makes it reasonable to assume they're independent?
It's just students. There's nothing to make me believe that if I pick a student who has a driver's license, that I'm more likely to pick another student that has a driver's license. That
Okay.
one is independent of the other. Now, let's say I'm trying to think of something that would be. I'm going to make up something ridiculous, but let's assume that. This is, I don't know, that we have, this town is the home of the A1 Driving School International. And so, because there are so many, they may not actually be independent of one another, because if their parent works for this, they may be more likely to have gotten a license, right? And if one has multiple children, then they may have, and so then they may not be independent of each other. That's not a very good example, but
No,
you
I understand it.
you kind of get, there may be other factors.
They don't mention those other factors though, so there's no point.
Right.
Okay.
Yeah, we can't know for certain, but I can't immediately think of something that would cause it not to be. All right, and then third, the success failure. So the predicted successes is going to be equal to 0.3 times 2,000. And you don't have to necessarily crunch this number. This one's not bad. That's 600. But if you just want to go, yeah, that's greater than or equal to 10. And the predicted failures is going to be 0.7 times 2,000, which is also greater than or equal to 10. So I've met all of the conditions. So I'm going to use a normal model where the mean proportion is 0.3, the mean percentage is 0.3. And then let's go back and look at our formula. It's the square root of PQ over N. So that's going to be the square root of 0.3 times 0.7 over 50.
So the mean and the probability, is that what P is again? Or no, success.
P is the proportion. Okay,
Proportion.
P is the probability that you're going to get a success.
Yes.
And Q is the probability you'll get a failure.
The mean and the probability of success are always the same.
Yes.
Okay.
Yes.
So that's the one that we have to memorize, right? And then whatever, like the points.
This one?
Yeah.
No, it's given.
Next to where do you go?
Where is it?
It says P times 1 minus P over N.
Yeah, but it's like the square root of everything, including.
Right, that is what I wrote in as well.
Oh, okay, sorry.
Too. Yeah, it's supposed to all be underneath the square root. I didn't draw my radical sign quite large enough. So let's see what this comes out to be. So instead of calculating it separately, I'm just going to go into the distribution. And this is a normal distribution where the mean proportion is 0.3, and this is going to be the square root of 0.3 times 0.7 divided by 50, and it gives me that is 0.0648. And I want the probability, that's a really bad normal curve, that we get 40% of the students. So the mean proportion should be 30%. We want the probability that more than 40%, that's what we're looking for.
It's weird how the normal curve, like, it's not 50% in the middle, you know? Like, even though that's not the, how do I say, like 50%.
Oh, yeah, it's
the
weird
bottom.
because you're doing percents of percents. Yeah. All right, so the probability that this is over 0.4, hang on a second. I gotta do over 0.4, is pretty small. The probability that p hat is less than, or excuse me, is greater than or equal to 0.4 turns out to be 0.0614.
How'd you figure that one out?
So let me pull, where is it? There it is. So I went to distributions,
Yeah.
and I went down to a normal distribution. On the TI, you'd be doing a normal CDF. I told it that the mean was 0.3. And the standard deviation was, I actually put that in. I did the square root of 0.3 times 0.7 divided by 50.
Yeah.
And then I want to know the probability that it's greater than, so I need to move this to more than 0.4.
So why would the 0.4 be on the other side?
Because 0.3 is the mean.
No, like you.
The 0.3 is the mean. So 0.4 has to be,
Yeah, but I mean, like, you know, how you put 0.4 in like the box that's in the bracket. Why
the,
would it-
whoa, the box that's in the bracket. Okay, yeah. Yes?
Yeah, so like, why would it be on the other side?
Why wouldn't what be on the other side?
The 0.4, like where the 0.06
0.3 is the mean though.
Yeah,
0.4 has to be to the right of that then.
like this thing here. Why wouldn't we put it in this box?
Because we want the probability that x is greater than 0.4. Just like I wrote here.
Oh yeah, sorry. That 'cause that's the
Probability that p
percentage.
hat is greater than 0.4.
That makes sense.
Yeah, and it's the same thing that Savannah was asking about. It's like, it feels weird a little bit because we're doing percentages and percentages, and that's part of why they call this the proportion.
Oh.
So yeah, the probability that the proportion of students is greater than 0.4 is gonna be something really, really
That
small,
makes sense. Yeah.
okay? And they are both percentages, and so it can be a little confusing. Once you get the hang of it, it's not too bad. So it's not very likely that if the true proportion is 30%, that we would get 40% of them. In fact, that probability is so low that if we got this from a sample, we would suspect one of two things has happened. Either it's not really 30% of the students, or somehow or another my sampling technique is flawed. Right? Because that's only about a 6% chance. That's not quite to the place where I'm immediately ready to go, no way. Typically, we're going to use actually, and we'll do this in the next section, typically we'll use 5% to be like, if it's, less than a 5% chance that that could have happened, just by chance, then I'm gonna say something's wrong. Okay? And we'll talk a lot more about that. Actually, it's later on in this section. But this is kind of leading us to that. So at this point, I'm like, that's an unusual sample, but it's not so unusual that I'm ready to, throw a flag on the play. Okay? All right, let's leave it there. And we will pick this up tomorrow.